Okay, so let's jump into this deep dive. Today we're looking at something that, well, it seems pretty practical on the surface. Estimating livestock water use.
Hmm.
Specifically when they're on land that's already irrigated.
Right, which adds a whole other dimension. It sounds like just, counting gallons.
Exactly. But it's way more complex.
It is. And what's really interesting and what our source material digs into is how this very real-world problem is actually a great way to think about some core math concepts.
Math. Okay, how so?
Well, the source is specifically trying to find good mathematical ways, formulations,
Mm.
using differentiation and integration, calculus,
Basically,
basically.
it's for cows drinking water.
Sort of, yeah.
Yeah.
The aim is to connect those, let's be honest, sometimes abstract calculus ideas to something, well, tangible, something college students learning this stuff can actually picture.
Okay, so our mission here is understanding that connection. How does a herd's thirst on a watered field connect to rates of change and totals? And what does this source actually say about how to model that? Because it's not like each animal just drinks, say, 5 gallons a day, fixed.
No, not at all. It's much more dynamic. Think about all the things that change it.
Like what?
Oh, temperature, obviously, time of day, how active the animals are, their size, the type of livestock.
Sure, a dairy cow versus a sheep.
Exactly. Even the type of grass they're eating. Maybe how recently the field was watered. The rate they drink water. It fluctuates a lot.
And managing that water is so critical, right? Especially on irrigated land. I mean, every drop is allocated for something.
You got to need water for the crops, absolutely. But you've also got to account for what the livestock are drinking so you don't mess up the whole balance, underestimate or overestimate.
Right.
And this is where the source says calculus can really shine. If you can model the rate of water consumption, maybe as a function of time or temperature,
Okay.
differentiation lets you analyze how sensitive that rate is. Like how much faster do they drink if it gets 5 degrees hotter?
Ah, okay. So you can pinpoint peak times or, say, the impact of a heat wave by looking at the derivative, the rate of change of the rate.
You're getting it. It's not just the average. It's how it's changing moment by moment.
That feels much more useful. So where does integration fit in?
Well, integration is for the total picture. If you have that rate model over time,
Like how many gallons per hour?
yeah, something like that. Integrating that rate function over a specific time, maybe a full day, or just those peak grazing hours that gives you the total volume of water they consumed.
I see. Total usage.
The source suggests this is really key for planning, for figuring out daily or weekly water needs for the herd.
Makes sense. Is it only about time, though? Could you, like, integrate over space?
That's a good question. Potentially, yes. Imagine a big field.
Mm.
Maybe the animals cluster in one area.
Or some parts have better grass, so they drink more there?
Right. You could, in theory, integrate consumption rates over the area to get a total for the whole field. The source kind of hints that figuring out these multi-variable models is part of the challenge.
So what's really insightful here, reading this source, isn't just saying, hey, use calculus.
No, it's more nuanced.
It's emphasizing the need for, like, clear and suitable mathematical ways to describe it all. Formulations, like you said.
Exactly. Capturing that dynamic reality, translating biology and weather into functions you can actually work with.
Using calculus tools.
That's the core idea from the source. Identifying this practical farm problem as a rich example, it shows that integrals and derivatives aren't just textbook exercises.
They're tools. Tools to solve real problems, like managing water efficiently
Taking the math off the blackboard.
and putting it out in the pasture. Literally helping measure how much water it takes to raise livestock on land we're already managing carefully. It shows math as a language, really.
Yeah, a language for describing the world, even parts you wouldn't immediately think involve complex math.
Okay, so let's wrap this up then. This deep dive, looking at this source, it shows estimating livestock water on irrigated land is, well, definitely not simple. It's complex, practical. And the source points to differentiation and integration as really crucial tools.
Tools for building models, right? Models that capture those changing rates and figure out the total water needed in that specific farming situation.
Mm-hmm.
So the key insight, really, is that the source uses this as a prime example, showing how fundamental calculus pops up in resource management where you might not expect it.
And it highlights why it's important to make those connections clear, to translate the real world into math.
It's about seeing the practical power hidden in the theory.
Well said.
All right, final provocative thought for you listening. We just talked about water use on a field. How many other everyday things around you, processes, resources, things that seem simple, might actually have an underlying mathematical structure? a structure you could maybe understand better using tools like calculus or other math you might be learning right now. Something to think about.